There are two main types of waves we studied while we used the Slinky. The first was the longitudinal wave. You created a longitudinal wave by pushing and pulling in the direction of the length of the Slinky, and the wave travel was along the length of the Slinky. So motion of particles in a longitudinal wave is parallel to the direction of the wave. We also created transverse waves. In order to make a transverse wave, you move your hand up and down perpendicular to the length of the Slinky, and the wave travels along the length of the Slinky. Motion of particles is perpendicular to the direction of the wave. Waves carry energy and nothing else. Just remember that. They only carry energy. To increase the amount of energy, you could increase either the amplitude or you could increase the frequency of the wave. Both increase the energy. Sound is an example of a longitudinal wave. The vocal cords produce sound and the ear receives sound. So we have areas that alternately spread out and compress in a sound wave and a longitudinal wave. Air is often the medium for the sound. It compresses and spreads out. Sound requires a medium such as air to travel through. In air, sound travels at about 340 meters per second at room temperature. As the temperature goes up, sound travels a little bit faster, but it is much, much slower than the speed of electromagnetic waves, of which light is an electromagnetic wave. So light and all other electromagnetic waves can travel in a vacuum. In space, all EM waves travel at 3 times 10 to the 8 meters per second. Now the waves travel as an interaction of electric fields and magnetic fields. Waves can interfere if they're in the same place at the same time. There are two types of interference. There's constructive interference, in which waves add together. You see the two smaller waves adding to an amplitude of a larger wave pulse. And then we have destructive interference, in which the amplitudes subtract. I have two examples. The first one is complete destructive interference. The second one here is partial destructive. I have a big wave and a smaller wave on the opposite side. They add to form a smaller wave. Once these waves interfere with one another, these pulses interfere, they continue on as if they had never met. Now, standing waves are a result of interference. And what I'm showing here are the dotted parts are antinodes, so let me mark those, and those are areas of maximum up and down motion. And then I have nodes, which are the dots on here, and they're areas of no displacement. Notice the incorrect spelling. So on this wave that I'm showing here, there are 4 antinodes and 5 nodes. I've also shown below that standing waves are harmonics. They're set up in pipes and on strings. On the left, it's the 3rd harmonic. On the right, it's the 4th harmonic. You kind of count what we call the Stewie heads to determine the harmonic number. Here's another example, the Doppler effect. The Doppler effect occurs for sound, and in fact light, when a source and receiver are getting closer together. So it appears that the pitch is increased. Say you're standing on tracks and a train is coming toward you. It appears whatever tone that the train is playing is increased to you, and then as it flies by, there's a sudden drop that you appear to hear, and that's decreased pitch. So it can occur both with sound and light. With light, it's usually a redshift with stars accelerating away from Earth. In order to measure the wavelength of a wave, you can go between 2 crests, which are here and here, or you could go between 2 troughs, I could also measure between this location and this location, or this location and this location. We also have the wave speed equation, which says wave speed is equal to frequency times wavelength. I hope this was a good review of waves for you. Good luck on the midterm.